pada tanggal 23 Oktober 1963. Hingga kini Departemen Teknik Sipil telah berkembang menjadi departemen yang besar dengan 3 program studi, 7 laboratorium, 13 tenaga pendidikan, 38 dosen pengajar, 640 mahasiswa aktif per tahun, serta lebih dari 4.000 alumni tersebar di belahan dunia.
Sebagai salah satu departemen pelopor di Fakultas Teknik Universitas Brawijaya, Departemen Teknik Sipil telah mengedepankan integritas untuk membangun pendidikan Indonesia di era Industri 4.0 and Society 5.0 melalui visi departemen yang menitik beratkan pada Sustainable Development. Tridharma perguruan tinggi yang kami terapkan tidak hanya berupa proses belajar mengajar secara formal, namun juga menanamkan karakter unggul dengan memanfaatkan segala fasilitas pendidikan yang mendukung berkembangnya potensi dan bakat mahasiswa. Lingkungan dengan suasana yang adaptif dan kolaboratif juga menjadi faktor krusial untuk menciptakan suasana belajar yang kondusif. Departemen Teknik Sipil tentu saja akan senantiasa mengikuti kemajuan ilmu pengetahuan dan teknologi untuk mencetak lulusan yang cerdas, kreatif, inovatif, berkarakter unggul, dan berdaya saing tinggi. Karakter unggul mahasiswa ini menjadi indikator prioritas pelaksanaan Tridharma perguruan tinggi di Teknik Sipil dalam rangka melahirkan insan akademis yang siap mengabdikan dirinya di tengah masyarakat melalui kompetensi keteknik sipilan.
Dalam pencapaian visi dan misi yang mengikuti perkembangan Laboratorium Mekanika Tanah dan Geologi, Laboratorium Manajemen Konstruksi, Laboratorium Kebencanaan, dan Studio Komputasi. 5 keminatan yang terdapat pada Departemen Teknik Sipil, yaitu struktur, keairan, geoteknik, transportasi, dan manajemen konstruksi, membekali mahasiswa untuk dapat bebas berkiprah dan sukses di berbagai profil lulusan di dunia kerja, seperti sebagai pegawai pemerintah, konsultan perencana, kontraktor, konsultan pengawas, akademisi, peneliti, maupun wirausaha. Untuk membantu kesuksesan program-program yang dijalankan, Departemen Teknik Sipil telah mempersiapkan berbagai fasilitas penunjang seperti ruang kelas dengan perlengkapan perkuliahan hybrid, laboratorium-laboratorium yang memadai, ruang baca dengan referensi khusus teknik sipil, ruang kerja mahasiswa S2 dan S3, akses internet yang cepat dan melingkup ke berbagai jurnal internasional bereputasi, ruang administrasi recording, auditorium, ruang sidang dan seminar, tempat berwirausaha civil corner, serta gazebo dan ruang diskusi indoor dan outdoor yang nyaman. Upaya peningkatan soft skill dan keterampilan mahasiswa turut terfasilitasi dalam berbagai kegiatan kokurikuler maupun ekstrakurikuler yang terdapat pada beberapa organisasi kemahasiswaan seperti HMS, Forsis, dan DPA dengan program kerja yang berintegrasi dengan program kerja unggulan departemen, yaitu program 3-in-1, Double Degree, Fast Track, Student Mobility, Staff Exchange, Joint Research, Seminar Internasional, MBKM, Dosen Berkarya, BKM Mahasiswa, Civil Fiesta, dan Civil Camp. Dalam rangka meningkatkan peran serta di masyarakat, dunia kerja, dan dunia pendidikan, Departemen Teknik Sipil terus meningkatkan kolaborasi kerjasama dengan perguruan tinggi, institusi, organisasi kemasyarakatan, dan lembaga penelitian baik tingkat nasional maupun internasional. Kolaborasi dari seluruh sivitas akademika yang bersinergi dan harmoni membuahkan berbagai torehan prestasi yang membanggakan baik pada bidang akademisi dan seni budaya pada tingkat nasional maupun internasional, seperti juara umum kompetisi jembatan Indonesia, juara 3 kompetisi bangunan tahan gempa IDERS Taiwan, penghargaan Asia Bridge Competition, dan berbagai penghargaan bergengsi lainnya. Hal ini menjadikan Departemen Teknik Sipil sebagai salah satu departemen yang favorit dalam penerimaan mahasiswa baru. Lahir sebagai departemen tertua di Fakultas Teknik, Departemen Teknik Sipil telah memiliki lebih dari 4.000 alumni, di mana tergabung dalam IKA TSIUB dengan Insinyur Destiawan Suwaryono MM selaku Ketua Umum IKA TSIUB, yang memiliki anggota dari berbagai alumni sukses yang tersebar di berbagai belahan dunia dengan berbagai disiplin kerja. Kunjungi kami di sipil.ob.ac.id dan kotak email kami melalui sipil@ob.ac.id. Kota Malang merupakan kota terbesar kedua di Provinsi Jawa Timur. Terletak pada ketinggian 440 meter di atas permukaan laut. Kota Malang memiliki iklim yang sejuk, panorama yang menarik, dan keramahan masyarakat menjadikan Kota Malang sebagai kota pendidikan yang paling diminati oleh calon mahasiswa dari dalam maupun luar negeri. Departemen Teknik Sipil adalah departemen yang pertama kali didirikan pada tanggal 23 Oktober 1963. Hingga kini, Departemen Teknik Sipil telah berkembang menjadi departemen yang besar dengan 3 program studi, 7 laboratorium, 13 tenaga pendidikan, 38 dosen pengajar, 640 mahasiswa aktif per tahun, serta lebih dari 4.000 alumni tersebar di belahan dunia.
Sebagai salah satu departemen pelopor di Fakultas Teknik Universitas Brawijaya, Departemen Teknik Sipil telah mengedepankan integritas untuk membangun pendidikan Indonesia di era Industri 4.0 and Society 5.0 melalui visi departemen yang menitik beratkan pada Sustainable Development. Tridharma perguruan tinggi yang kami terapkan tidak hanya berupa proses belajar mengajar secara formal, namun juga menanamkan karakter unggul dengan memanfaatkan segala fasilitas pendidikan yang mendukung berkembangnya potensi dan bakat mahasiswa. Lingkungan dengan suasana yang adaptif dan kolaboratif juga menjadi faktor krusial untuk menciptakan suasana belajar yang kondusif. Departemen Teknik Sipil tentu saja akan senantiasa mengikuti kemajuan ilmu pengetahuan dan teknologi untuk mencetak lulusan yang cerdas, kreatif, inovatif, berkarakter unggul, dan berdaya saing tinggi. Karakter unggul mahasiswa ini menjadi indikator prioritas pelaksanaan Tridharma perguruan tinggi di Teknik Sipil dalam rangka melahirkan insan akademis yang siap mengabdikan dirinya di tengah masyarakat melalui kompetensi keteknik sipilan.
Dalam pencapaian visi dan misi yang mengikuti perkembangan dunia industri Republik Indonesia 4.0 dan Society 5.0, Departemen Teknik Sipil didukung oleh 3 program studi, yaitu program studi sarjana, program studi magister, dan program studi doktor yang telah terakreditasi unggul BAN PT. Departemen Teknik Sipil senantiasa memastikan proses dan kualitas Tridharma perguruan tinggi, yaitu pendidikan, penelitian, dan pengabdian kepada masyarakat berjalan dengan baik sesuai standar nasional perguruan tinggi dalam Permendikbud 3 tahun 2020 dan standar internasional Washington Accord serta ISO 9001-2015 dan ISO 21001-2018 melalui monitoring dan evaluasi dalam siklus PPEPP. 7 laboratorium yang berada di Departemen Teknik Sipil guna memfasilitasi mahasiswa dalam meningkatkan pemahaman kognitif dan psikomotorik untuk pemenuhan capaian pembelajaran lulusan sesuai dengan kurikulum berbasis Outcome Based Education atau OBE yang diterapkan dengan mempertimbangkan masukan Asosiasi Teknik Sipil BMPTT SSI, yaitu Laboratorium Struktur dan Bahan Konstruksi, Laboratorium Transportasi dan Jalan Raya, Laboratorium Pemetaan dan Penginderaan Jauh, Laboratorium Mekanika Tanah dan Geologi, Laboratorium Manajemen Konstruksi, Laboratorium Kebencanaan dan Studio Komputasi. 5 keminatan yang terdapat pada Departemen Teknik Sipil, yaitu struktur, keairan, geoteknik, transportasi, dan manajemen konstruksi, membekali mahasiswa untuk dapat bebas berkiprah dan sukses di berbagai profil lulusan di dunia kerja, seperti sebagai pegawai pemerintah, konsultan perencana, kontraktor, konsultan pengawas, akademisi, peneliti, maupun wirausaha. Untuk membantu kesuksesan program-program yang dijalankan, Departemen Teknik Sipil telah mempersiapkan berbagai fasilitas penunjang seperti ruang kelas dengan perlengkapan perkuliahan hybrid, laboratorium-laboratorium yang memadai, ruang baca dengan referensi khusus teknik sipil, ruang kerja mahasiswa S2 dan S3, akses internet yang cepat dan melingkup ke berbagai jurnal internasional bereputasi, ruang administrasi recording, auditorium, ruang sidang dan civil corner, serta gazebo dan ruang diskusi indoor dan outdoor yang nyaman. Upaya peningkatan soft skill dan keterampilan mahasiswa turut terfasilitasi dalam berbagai kegiatan kokurikuler maupun ekstrakurikuler yang terdapat pada beberapa organisasi kemahasiswaan seperti HMS, Forsis, dan DPA dengan program kerja yang berintegrasi dengan program kerja unggulan Departemen, yaitu program 3-in-1, Double Degree, Fast Track, Student Mobility, Staff Exchange, Joint Research, Seminar Internasional, MBKM, Dosen Berkarya, PKM Mahasiswa, Civil Fiesta, dan Civil Camp. Dalam rangka meningkatkan peran serta di masyarakat, dunia kerja, dan dunia pendidikan, Departemen Teknik Sipil terus meningkatkan kolaborasi kerjasama dengan perguruan tinggi, institusi, organisasi kemasyarakatan, dan lembaga penelitian baik tingkat nasional maupun internasional. Kolaborasi dari seluruh sivitas akademika yang bersinergi dan harmoni membuahkan berbagai torehan prestasi yang membanggakan, baik pada bidang akademisi dan seni budaya pada tingkat nasional maupun internasional, seperti juara umum kompetisi jembatan Indonesia, juara 3 kompetisi bangunan tahan gempa Leaders Taiwan, penghargaan Asia Bridge Competition, dan berbagai penghargaan bergengsi lainnya. Hal ini menjadikan Departemen Teknik Sipil sebagai salah satu departemen yang favorit dalam penerimaan mahasiswa baru. Lahir sebagai departemen tertua di Fakultas Teknik, Departemen Teknik Sipil telah memiliki lebih dari 4.000 alumni, di mana tergabung dalam IKA TSIUB dengan Insinyur Destiawan Suwaryono MM selaku Ketua Umum IKA TSIUB yang memiliki anggota dari berbagai alumni sukses yang tersebar di berbagai belahan dunia dengan berbagai disiplin kerja. Kunjungi kami di sipil.ob.ac.id dan kotak email kami melalui sipil ub.ac.id. Kota Malang merupakan kota terbesar kedua di Provinsi Jawa Timur. Terletak pada ketinggian 440 meter di atas permukaan laut. Kota Malang memiliki iklim yang sejuk, panorama yang menarik, dan keramahan masyarakat menjadikan Kota Malang sebagai kota pendidikan yang paling diminati oleh calon mahasiswa dari dalam maupun luar negeri. Departemen Teknik Sipil adalah departemen yang pertama kali didirikan pada tanggal 23 Oktober 1963. Hingga kini, Departemen Teknik Sipil telah berkembang menjadi departemen yang besar dengan 3 program studi, 7 laboratorium, 13 tenaga pendidikan, 38 dosen pengajar, 640 mahasiswa aktif per tahun, serta lebih dari 4.000 alumni tersebar di belahan dunia.
Sebagai salah satu departemen pelopor di Fakultas Teknik Universitas Brawijaya, Departemen Teknik Sipil telah mengedepankan integritas untuk membangun pendidikan Indonesia di era Industri 4.0 and Society 5.0 melalui visi departemen yang menitik beratkan pada Sustainable Development. Tridharma perguruan tinggi yang kami terapkan tidak hanya berupa proses belajar mengajar secara formal, namun juga menanamkan karakter unggul dengan memanfaatkan segala fasilitas pendidikan yang mendukung berkembangnya potensi dan bakat mahasiswa. Lingkungan dengan suasana yang adaptif dan kolaboratif juga menjadi faktor krusial untuk menciptakan suasana belajar yang kondusif. Departemen Teknik Sipil tentu saja akan senantiasa mengikuti kemajuan ilmu pengetahuan dan teknologi untuk mencetak lulusan yang cerdas, kreatif, inovatif, berkarakter unggul, dan berdaya saing tinggi. Karakter unggul mahasiswa ini menjadi indikator prioritas pelaksanaan Tridharma perguruan tinggi di Teknik Sipil dalam rangka melahirkan insan akademis yang siap mengabdikan dirinya di tengah masyarakat melalui kompetensi keteknik sipilan.
Dalam pencapaian visi dan misi yang mengikuti perkembangan Laboratorium Mekanika Tanah dan Geologi, Laboratorium Manajemen Konstruksi, Laboratorium Kebencanaan, dan Studio Komputasi. 5 keminatan yang terdapat pada Departemen Teknik Sipil, yaitu struktur, keairan, geoteknik, transportasi, dan manajemen konstruksi, membekali mahasiswa untuk dapat bebas berkiprah dan sukses di berbagai profil lulusan di dunia kerja, seperti sebagai pegawai pemerintah, konsultan perencana, kontraktor, konsultan pengawas, akademisi, peneliti, maupun wirausaha. Untuk membantu kesuksesan program-program yang dijalankan, Departemen Teknik Sipil telah mempersiapkan berbagai fasilitas penunjang seperti ruang kelas dengan perlengkapan perkuliahan hybrid, laboratorium-laboratorium yang memadai, ruang baca dengan referensi khusus teknik sipil, ruang kerja mahasiswa S2 dan S3, akses internet yang cepat dan melingkup ke berbagai jurnal internasional bereputasi, ruang administrasi recording, auditorium, ruang sidang dan seminar, tempat berwirausaha civil corner, serta gazebo dan ruang diskusi indoor dan outdoor yang nyaman. Upaya peningkatan soft skill dan keterampilan mahasiswa turut terfasilitasi dalam berbagai kegiatan kokurikuler maupun ekstrakurikuler yang terdapat pada beberapa organisasi kemahasiswaan seperti HMS, Forsis, dan DPA dengan program kerja yang berintegrasi dengan program kerja unggulan departemen, yaitu program 3-in-1, double degree,
Assalamualaikum warahmatullahi wabarakatuh. Shalom, Om Swastiastu, Namo Buddhaya, Good Will Wishes, Good Morning, and Best Wishes to all of us. Dan Rebel Mr. Insinyur Eko Andi Suryo STMT PhD as the head of the Department Civil Engineering Faculty of Engineering Brawijaya University. Dan Rebel Mrs. Dr.
Recording in progress.
Engineering Insinyur Eva Arifi STMT as the head of undergraduate study program Department of Civil Engineering Faculty of Engineering Brawijaya University. Dan Rebel Professor Keisuke Murakami PhD from Miyazaki University Japan as the speaker today. Dan Rebel Mr. Himamul A'la STMT as the moderator of this event today. Dan Rebel lecturers who join Civil Webinar 2023 today. And we will also greet welcome to all attendants in the event Civil Webinar 2023 with the theme Basics of Water Wave. Praise be to the Almighty because thanks to His grace we can gather at the Civil Webinar 2023 today. May we will always be under His protections. Amin. Before we go any further, let me introducing myself. My name is Helen Herista as the Master of Ceremony who will be hosting today's event. Before the event begins, please allow me to read the rules and regulations that must be obeyed during the event. The first participants are required to change the name format in accordance with the provisions, namely full name underscore name. During the event, participants are expected to activate the camera and use the virtual background that has been provided. Participants are required to turn off the microphone feature when it is not in use. Participants wear net formal attire. Participants who wish to ask questions can use the raise hand feature and ask their questions directly after being invited, or can send them in the chat column. And the last, participants are required to fill in attendance data via the attendance links by attaching screenshot evidence of activities for attendance purpose and making a certificate. Ladies and gentlemen, please allow me to read the schedule of this morning sessions, which will begin with the opening and recitations of prayer, followed by a series of remarks, after which we will go to the material presentation sessions and question and answer sessions. Then we will close with prayer and documentations. So ladies and gentlemen, to begin this morning session, let us recite a prayer that will be led by Davasya Panditya. Welcome Davasya, time is yours.
Thank you for the opportunity. Assalamualaikum warahmatullahi wabarakatuh. Let us lower our gaze for a moment, pray for the blessing of Allah Subhanahu wa Ta'ala, God Almighty, so that our activities today will be given ease. Allow me to lead the prayer in the Islamic way. For attendees of other religions and beliefs, please adjust to their respective beliefs. For those who are Muslim, let us start our prayer by reading the Quran Al-Fatihah. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Ar-Rahmanir-Rahim. Maliki yaumiddin. Iyyaka na'budu wa iyyaka nasta'in. Ihdinas siratal mustaqim. Siratal ladzina an'amta 'alaihim ghairil maghdubi 'alaihim waladdallin. Amin. A'udzubillahi minasyaitonir rajim. Bismillahirrahmanirrahim. Hamdan syakirin, hamdan na'imin. Hamdan yuafi ni'amahu wa yukafi mazidah. Ya Rabbana lakal hamdu kama yanbaghi li jalali wajhikal karimi wa azimi sultanik. Allahumma sholli wa sallim ala sayyidina Muhammad wa ala alihi wa ashabihi ajma'in. Asyhadu an la ilaha illallah wa asyhadu anna Muhammadan abduhu wa rasuluh. O Allah, our Lord, all praise to be to you for the mercy and grace that you have bestowed upon us, for the blessings of health and the opportunity so that we can gather to carry out the 2023 civil webinar activities today. Therefore, O Allah, make our event a success, bless and fill this meeting with goodness from beginning to end. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzabannar. Sallallahu ala sayyidina Muhammad wa ala alihi wa ashabihi ajma'in. Walhamdulillahirabbil alamin. Thank you.
Amin, amin, ya Rabbal Alamin. Thank you to Davasha. Hopefully all of us who listen can get blessings. Furthermore, remarks will be delivered by the head of Department of Civil Engineering, Faculty of Engineering, Brawijaya University, Mr. Insinyur Eko Andi Suryo, STMT, PhD. Time is yours.
Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. On behalf of the Department of Civil Engineering, I would like to welcome all the participants and thank you for your presence, especially for Professor Keisuke Murakami from University of Miyazaki. We are very happy to have you here with us. Even though this meeting is still online, but I believe it will not decrease our enthusiasm to follow. I also apologize because now I have to go to the police stations to get my driving license, and therefore I recorded my opening remarks in this video. I believe this seminar will give many beneficial knowledge for the students and also the participants. The topic of water is one of the main things we learn in the field of civil engineering. As we know, water has benefit, also has the potential for cause damage. For example, on natural slopes, infrastructure, and also in any constructions. And by understanding the basic characteristics of water flow, it will be an asset for us to control and also to reduce the potential for the damage. Finally, I would like to congratulate you all to join this seminar. And once again, thank you for Murakami Sensei for your kindness and also for your knowledge that will be shared in this meeting. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Well, thank you, Mr. Insinyur Eko Andi Suryo, STMT, PhD, for the welcome you have given. Okay, before we begin, let us introduce the speakers of today's Civil Webinar 2023. Let me introduce our speaker today is Professor Keisuke Murakami, PhD from Miyazaki University, Japan. He is a professor from Department of Civil and Environmental Engineering, Miyazaki University, and also Vice President, International Relations, Miyazaki University. He is graduated from Kyushu University, Faculty of Engineering at 1985, with specialty coastal engineering and disaster prevention engineering. Professor Keisuke Murakami, PhD, also has several written works, such as a journal with the title Effect of Wind Speed on Wavefront Upheave of Irregular Waves and Investigations through Hydraulic Experiment 2023, and Effect of Exhaustive Topography in Coastal Area on Mitigations of Tsunami Hydraulic Force 2023, Characteristic of Wavefront Upheave under Wind Actions 2023, Numerical Study on Sedimentation's Problem near the Entrance to Marina Channel in Miyazaki Port 2022, Study on Sedimentations along Marina Channel in Miyazaki Port 2021, and also physical and numerical simulations of wave transmissions over submerged breakwater 2021. Wow, what a great speaker we had this morning. He is very experienced and has a high understanding of water research engineering, which is the theme of our civil webinar this morning. Therefore, it is hoped that all participants can listen well to the valuable knowledge that will be presented by our guest speaker. Here we have followed together a series of remarks. Moving on to the next event, we will enter to the most awaited sessions, the presentations of material, which will be presented by Professor Keisuke Murakami, PhD from Miyazaki University, Japan. The presentations of the material will be given by Mr. Himamul A'la, STMT, as moderator. To Mr. Himamul A'la, STMT, time is yours.
Okay, thank you. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Our honored keynote speaker, Mr. Professor Keisuke Murakami, PhD, from University of Miyazaki, Japan, and head of undergraduate program, Civil Engineering Department, Dr. Engineering FREP, and our fellow lecturer, student, and all participants. For this occasion, we will have a webinar entitled Basic of Weather Wave. We are going here for learn more from Professor Keisuke Murakami, PhD. Hello, Mr. Professor. How are you? Can you hear me?
Yes. Hello. Good morning.
Okay, thank you. I hope you and your family are in a good condition.
Thank you very much.
Okay. Is the weather good there, Mr. Professor?
Yeah, here it's very cold.
Very cold.
Good morning, Sensei. How are you, Sensei?
Dr. Miko-san. How are
Yes. How are you? Nice to see you again.
you? Nice to see you. Okay.
Yes, and if you have time, please also come to our university in person.
Yeah, thank you very much. So I hope so. I want to visit Brawijaya again.
And our student also want to have an opportunity for Sakura in Miyazaki also.
Yes. So that is a good program. So I want to try again. Okay.
Yes, thank you very much for your time.
Yes, thank you very much.
Okay. So, Mr. Professor, the time for you for delivering the material. Your material is about 75 minutes. After
Okay.
that, we have a discussion section in 20 minutes, and the last one is conclusion from you.
Okay.
And before we start our webinar, I remind to all participants, please prepare your notes because we will gain a lot of knowledge here. So please maintain your focus during the presentation. All right, Mr. Professor Keisuke Murakami, the time is yours.
Okay. I will start. Okay. Is it okay? The slide is, can you see my slide? Okay.
Yes, we can.
Okay. Good morning, everybody. My name is Keisuke Murakami, the professor of the Faculty of Engineering in University of Miyazaki, Japan. So my major is coastal engineering, and this is related to the hydraulic engineering. Maybe in Brawijaya universities, the faculty of civil engineering never have this kind of topic. But today, so I try to introduce the basics of wave motion. Okay. So today, so I'd like to talk about, first of all, the introduction of the University of Miyazaki. And after that, so I will talk about today's topic, basics of wave motion. Okay, I will talk about my universities. University of Miyazaki is a national university, one of the national universities. This is one of the photo in my campus. And our motto is look at the world and start with the community. This is our motto, okay? Our slogan. So my university was established 1949. So the beginning of the university start with 3 faculties: engineering, agriculture, and education. And also, 1974, the Miyazaki Medical College was established. And after that, 2004, my universities and Miyazaki Medical University was integrated. And 2005, University of Miyazaki started as a national university corporation. So the number of the students around more than 5,000, and academic staff and administrative staffs are around more than 2,200. And Miyazaki is one of the famous prefectures as the production of the food, chicken, beef, mango, oranges. These are #1 production in Japan. Especially the mango is very expensive, very, very expensive compared with Indonesian mango. So I never eat that. The location, I want to introduce the location of my university. Where is the University of Miyazaki? So you know that this is a Japanese island. There is a main island, including Tokyo, and Hokkaido, the northern part of Japan. And Miyazaki is on the southern island, Kyushu Island here. This is a Kyushu Island. And there are some prefectures, and my university is located in the Miyazaki prefecture here. My university is just here. This is an aerial photo of my campus. Around 10 kilometers from city area. Okay. Surrounded by the nature. Very nice and comfortable campus. Okay. If you have the chance to visit Japan, so please come to Miyazaki and enjoy the very nice environmental space. And this is the structure of education in my university. There are 5 undergraduate courses here: education, regional innovation, medicine, engineering, and agriculture. After finishing this undergraduate course, so many students go into the graduate school, master course. There are 5 master courses. And after that, 2 years education, so some students go into the doctor course, graduate school. There are 2 doctor courses in my university. One of the doctor course is Interdisciplinary School of Agriculture and Engineering. And another one is Interdisciplinary School of Medicine and Veterinary Medicine. There are 2 doctor courses. Okay. Of course, so many students studied these courses from another universities and international universities. You know that many students from Bulgaria also studied in those courses. Okay. This is the outline of my universities. If you are interested in my universities, please contact me or please contact Dr. Nico. Okay. Okay. We move to today's topic. Basics of wave motion. So today, I want to talk about the waves, especially the wave theory. Okay. You know that sea waves are categorized into some characteristics of wave. Especially, we sometimes categorize based on the frequency of the wave. So when we go to the beach, so we usually see the gravity wave. The period is few seconds or 10 seconds or more than 10 seconds. This is the main waves we usually see on the beach. And also the relative energy is higher than other waves. The gravity waves was generated by the wind. And less than 1 second, these are very short waves, ripple waves or capillary waves. These energies are very small, and in engineering, so we usually neglect these waves because the wave energy is very small. On the other hand, longer waves, such as a tide or long period waves and long gravity waves, these are very important in the design of coastal structure. Especially, the tide is one of the important waves. 12 hours period. This is very important and basic waves when we design the structure. Basic information of in the wave structure design. And also long period waves such as tsunami and storm surge. This is also the important waves related to the coastal disaster. It has a very long wavelength and large wave energy. Okay, but today, so I will talk about mainly the theory of gravity waves. Okay, this is waves in front of the Miyazaki prefecture. So we usually see the waves coming from offshore to onshore, and waves usually breaks near the coastal area. We call this as breaking waves or breaker waves. So today, so I will talk about the theory of the waves before breaking. Okay, this is a experimental wave motion I measured here. This is a normal waves, usual waves, periodic waves, but this is tsunami waves, much longer waves and much longer period. So today's topic is normal waves above these movies, upper part of these movies, and this is a kind of periodic waves. Okay, before talking about the wave theory, so I will show you the definition of the symbols I used in this today's lecture. Usually, today's talking, so sometimes I use capital H here. This one, this is we call wave height, and eta. This is the temporal water surface location. Eta is the temporal water surface location, and capital L is the wavelength, and H is the water depth. Okay, and in this theory, so I take the origin of the coordinate on the mean water surface level here. And upper direction, V, and lateral direction, A. Okay. This is the main symbols I will use in today's lecture. Also, I forgot. Wave speed. Capital C is a wave speed. Okay. And roughly speaking, there are two kinds of wave. One is a regular wave. I show you the previous slide, movies. This is a kind of the sinusoidal wave, regular wave. And other one is an irregular wave. It has a random wave height, like this one. This is a kind of natural wave. Natural waves we can see on the beach is categorized in irregular waves. But irregular waves are composed with regular waves. You know that Fourier expansion, maybe you learned in the mathematics. Fourier expansion means, Fourier series means random function can be shown with a sum of the sinusoidal function. Okay, so that is why understanding regular waves is very important. Okay, today I will talk about regular waves. If you can understand the characteristics and the theory of regular waves, you can easily understand the irregular waves. Okay, at the beginning of the theory, there are some assumptions. So today I will talk about linear wave theory, and this theory includes some assumptions. One of the assumptions is two-dimensional phenomenon. And second one is a small amplitude oscillation. And third one is, this is important one, irrotational motion. And no viscosity and incompressible flow. And I mentioned the theory is based on sinusoidal waveform. And the sea bottom is a flat and permeable. Okay. And another, these red colored assumption is a very important assumption. And other one is constant atmospheric pressures and wave propagate without changing its form and neglect Coriolis force. So introduction of velocity potential based on the assumption of irrotational motion. So on next slide, I will talk about more detail. But in this theory, we introduce the velocity potential, the concept of velocity potential. So U and W, these are the velocity in X direction and velocity in Z direction. And these velocities is derived from the velocity potential phi, okay, differentiated by X or Z. This is the definition and introduction of the velocity potential, okay? Okay, then next I will talk about what's the meaning of irrotational motion. This is an image of the water particle rotation, okay? This blue, green colored water particle, just rotating like this one, clockwise rotate. And this kind of rotation is generated by the flow velocity, left-hand side and right-hand side here. The left-hand side is larger than right-hand side. this water particle has a clockwise rotation. Okay. And so we try to take the difference of velocity on left-hand side and right-hand side, like this one, and take a limit delta x getting smaller and approach to 0. So we can have the derivatives of w by x. Okay. The same things we try to take horizontal direction. Okay. Here is u and upper side u and lower side u. And upper side u is faster than lower side. So water particle rotate on clockwise direction. Okay. So in this case, so in the same manner as left-hand side, so try to take the difference of velocities and divide it by delta z, and delta z goes to 0. We can have the differential form of u by z. So the greater the speed difference, the stronger the rotation. Okay. This is a water particle rotation, image of the water particle rotation. Okay. So that is why the vorticity, the strength of the water particle rotation, okay, degree of strength that causes fluid particles to rotate. This is the definition of the vorticity. So from this definition, we can have the vorticity like this one. Counterclock this part and this part. Okay, this is the vorticity. If we assume the irrotational motion, so this vorticity equals to 0. No vorticity. This is a definition of the irrotational motion. Okay. In the wave theory, we use this assumption. Okay, maybe you can understand this one. Okay, the practice. Let's deliver the following relational expression. I show you the previous slide. Take the difference of z direction velocities and divide it by x, and take a limitation x goes to 0. So this is results of this definition. So, but how you can get this relation? Can you derive from left-hand side to right-hand side? Can you do that? Please try this one. Please try. Maybe you can easily derive the right-hand side of this equation. Okay? Is it possible? Can you do that? Okay, I will show you. So you need to use Taylor expansion. Taylor expansion, okay? Sorry, this is a mistake. Taylor expansion. So please correct this one. This is a mistake. On this equation, you can expand with using Taylor expansion. W is a vertical direction velocity. X plus delta x z can be expressed as a Taylor expansion like this one. Okay. Maybe you know this kind of expansion. And you put this relation in here, so you can rewrite this kind of relation and divide it by x and neglect the second order part because we are now considering the linear problem. So that is why we neglect this part. This part is much smaller than first order. Second order is much smaller than first order. Okay. Okay, so from this, we can derive this relation. And the horizontal direction is the same. You can derive the horizontal direction relation with using these Taylor expansion. Okay, the next is the image of the velocity potential. This is vorticity defined previous slide. And based on the assumption of irrotational motion, so I showed you the result of the irrotational motion. So in this case, so we introduce the velocity potential phi here and here. And when you derive the horizontal velocity, so you differentiate phi by x, and also you derive the vertical direction velocity. So you differentiate phi by z. If you can introduce this kind of velocity potential, so we can satisfy this irrotational motion like this one. So you put this part in here and this part in here. So you can have this vorticity equals to 0. Okay. This is the image of this is the introduction of the velocity potential. And image is here. Here is a mountain. Okay? And the height of the mountains is a kind of the intensity of the velocity potential. Okay? And this part and this part means the slope of the mountain, okay? X direction or Z direction, okay? If you have the steep slope, the velocity becomes higher. And if you have the gentle slope, the velocity becomes lower, okay? This is the image of the velocity potential. And the advantages of introducing velocity potential. There is advantages, okay? When you talk about wave theory, because U and W can be expressed by the velocity potential phi. So that is why you can reduce the number of unknowns to solve. Okay. If we don't introduce the velocity potential, we have to solve U, W, P. There are 3 unknown parameters. But after you introduce the velocity potential phi, unknown parameters become phi and p. P is a pressure. There are two unknown factors because U and W can be derived from phi. This is a very big advantage. We can reduce the number of unknown parameters. Okay? So that is why we introduce the velocity potential in the wave motion. Okay, the next, so we try to talk about the governing equation. Governing equation. Maybe I think you already understand this one. Continuity equation. Okay, in fluid dynamics, this is a basic understanding of the one of the governing equations. Okay. This is a small water particle. Small water compartment here. dx, dz is size of the compartment here. And some amount of water go into this compartment and some amount of water go out from this compartment. Inflow from left-hand side or lower side and outflow from upper side or right-hand side. So the size of the compartment is dx and dz. So you can, when you write the mass of the water inflow is rho u dz. So outflow can be expressed with using Taylor expansion, like this one. And in vertical direction, when you set mass of inflow, rho w dx, so you will have the outflow like this one with Taylor expansion. So based on the concept of continuity equation, so sum of the mass flowing in and flowing out from each side equals to 0. So this can be right as this equation. Outflow, inflow, outflow, inflow, the sum of the flow in and out equals to 0. Okay. From this, so you can have the continuity equation like this one. This is maybe you already know this one. Okay. And next is momentum equation. So we say Euler's equation of motion. Okay. And so in the assumption, so as I mentioned before, so we cannot consider the tangential force tau. Okay. We neglect this force and only consider the pressure and gravity. So first of all, so you understand the external force acting on the fluid element. This is a fluid element, okay? And on left-hand side, pressure P acting on this face, and area is dA. PdA is external force on left-hand side, and right-hand side also have the external force expressed by this one with using the Taylor expansion. This is the external force on the right-hand side. And this part is a gravity forces acting on minus z direction. Okay. So you clear each external forces acting on this element and summarize like this one. Okay. And next is the acceleration of the fluid element. Okay. Acceleration. Okay. Acceleration means the change of the velocities from here to here. Here to here. Okay. It takes delta t move from here to here. Okay. This is velocities on this side, on right hand side, and v is left hand side velocity. Okay. Here is v, and here is this part. This is derived from the Taylor expansion again. Okay. So after summarizing this formula, so you can have the acceleration of fluid element like this one. So and so as you know that we apply the Newton's second law. This is momentum forces the fluid element has. This is a velocity, this is acceleration, and here is the mass of the fluid element. This is the inertia part here. This inertia part R equals to the external forces. Okay. This is Newton's second law. So from this, you can have the famous momentum equation, Euler's equation of motion, like this one. You summarize from here to here. And from this equation of motion, by introducing the velocity potential phi in V, you can get this part, this formula. And this formula means this part derived by S equals to 0. This means that this part is a constant. Okay. This part is a constant. Okay, constant. This is a famous theory, Bernoulli's theory. Okay, we use this theory in next as a next derivation of the theory. This is a theoretical treatment. Okay, so we derive the continuity equation like this one, and we introduce the velocity potential U and W like this one, and you put U here, this part, and W, you put this part in here. You will get this equation related to the velocity potential phi. This is a famous equation, Laplace equation. Laplace equation. This equation can be solved by applying the boundary condition. Okay. So in this theory, so you can use this waveform because wave motion is a sinusoidal. So Eta is a temporal water surface location, like this one. This is a temporal sea surface form, and this is expressed by the sinusoidal function. So we use here cosine function. And K and sigma are wave number and angular frequency related to wavelength L and wave period T. So maybe it is important to understand this part, kx minus sigma t. So from this expression, these waves expressed as a progressive wave. Okay? Focus on the point here. Here, with wave propagation, wave moves like this one. But the phase of this point is always the same. Okay? Always the same. Okay? This means that the kx minus sigma t, this part, is a constant. Okay? With the wave propagation, waveform move here, and you focus on the same phase point here. This is a same phase point. So same phase point means kx minus sigma t is a constant. So now, kx sigma t is expressed as theta, and you take that derivatives of the theta by t. So theta is a constant. So if you take the derivative of t, so this is equal to 0. Okay. dt dx. So you summarize this equation, and dt dx, this is the speed of the waveform. Okay. Is k divided by sigma divided by k. This means that the L divided by t. So this means this is wave speed. Okay. So that is why progressive sinusoidal waves can be expressed as this form. And h is a wave height, and wave height divided by 2, a half of the wave height equals to the amplitude. So this form represents traveling wave that propagate in the positive direction, c, because c is a positive value. Okay? Positive direction of the x-axis at the wave speed c. Positive. This because this is a positive number. Okay, if you take this form, not kx minus sigma t, but kx plus sigma t. So what the meaning of this form? Okay. In the same manner as previous slide, theta equal to kx plus sigma t, and you take a derivative of theta by t. In this case, t has a negative value. Okay. Here is a minus sign here. Okay. This means that when you use this kind of expression for the waveform, so this means that the waves propagate to the negative direction of the x-axis. So by understanding these waveforms, so we try to solve the Laplace equation by applying the boundary condition. So this is a governing equation, Laplace equation. Okay. And so we check the boundary condition one by one. Okay. The boundary condition on the C bottom. The C bottom is impermeable. So impermeable means the velocity in z direction equals to 0. In another expression, with using the velocity potential, this means impermeable condition. Velocities in z direction equals to 0. Okay. On the other hand, the boundary condition on the C surface. On the C surface, so pressure equals to 0. P is water pressure. Okay, on the water surface, no water on the water surface. So that is why P equals to 0. Okay, and we derive the Bernoulli equation here and neglect the nonlinear part, square of u, square of w. These are the nonlinear part. We neglect this part because we are now deriving the linear theory. So after neglecting this part, we have the boundary condition on the water surface. Okay, z equals to eta, and phi is the velocity potential. So from this, so the water surface elevation, eta, can be expressed as this form. And another water surface boundary condition, on the water surface, there is a vertical direction velocity w equals to the speed of the water surface motion, okay? Water surface elevation. Water surface elevation moves up and down, and this is equal to the water particle velocities on the water surface. Okay. So these are the boundary conditions on the water surface. Okay. The boundary condition on the water surface is applied at z equals 0 due to the reason of the small fluctuation of the water surface. Though the boundary condition should be applied, sorry, this is eta. This is mistake, eta. Actually speaking, the location of the water surface is eta, this one, but now we are assuming the water surface fluctuation is small near the z equals 0. So that is why we apply the boundary condition z equals to 0 after that. Okay, just try to solve the problem. This is a waveform I mentioned before, traveling to the x positive direction. And this is a boundary condition on the water surface. From these two relations, we can assume the velocity potential like this one. Okay, because the water surface eta has a cosine function, and when you take the derivatives of phi by t equals to cosine function, so you can assume this form. Okay, so please put phi in here. Maybe you can get this equation, above equation. So in this equation, fz is an arbitrary function that becomes 1 at the z equals to 0. Okay. So we have to define, we have to find the form of this part. Okay, we put this form in Laplace equation here. You will get this form. This is a second order linear differential equation. This is a famous equation. And you can solve this one by assuming this form. A and B are the integral constants. Okay? So this red color form can be expressed as this one. And on the boundary condition on the C bottom, I mentioned before here. So you can have the relationship between A and B. Okay? A and B. A equals B times exponential of 2kh. Okay? And you put this relation in previous equation, you will have this one. And in this expression, we use this kind of relation, okay? Cosine hyperbolic and sine hyperbolic. These are the hyperbolic functions defined as the exponential relation, like this one. Also, you apply another C surface boundary condition. So from this, you can have the relation with B. You can decide the form of the B. So finally, finally A and B are decided. So we have the final form of the velocity potential like this one. Okay. And next is this is a solution of the Laplace equation. Okay, this is a solution of the Laplace equation. So next is we talk about the dispersion relation with using this solution. These two are the boundary conditions on the water surface here and here. From these, so you put this part in here. So you will have this differential equation, okay? You will have this, you can have this differential equation. I'm putting this solution in here, 5. So, and z equals to 0 because these are the conditions on the water surface. So from this, so you will have this important relation. Square of sigma. Sigma is angular frequency equals to z times k times hyperbolic tangent kh. K is a wave number and h is a water depth. This is a famous characteristics of the hyperbolic function. Cosine hyperbolic, sine hyperbolic goes to infinity when kh goes to larger values, but when kh goes to 0, cosine hyperbolic takes 1, and sine hyperbolic goes to kh. And tangent hyperbolic here goes to unity, goes to 1 when kh goes to the larger value, and when kh go to 0, it approached to kh. Okay. So I talk kh, but k is a wave number and kh is a relative wave water depth, because h is a water depth and l is a wavelength. Okay. From these characteristics of the hyperbolic function, this one, when we talk about the deeper water wave, when the kh goes to infinity, this form goes to this one. Okay, the wavelength directly related to the square of wave period. So deep water cases, this form never include the water depth h. And the wave speed equals to 1.56 times t from this equation. This is the assumption of deeper wave, k equals to infinity. On the other hand, kh goes to 0. This means shallow water wave. So tangent hyperbolic goes to kh. Okay. So that is why here goes to kh. So the wavelength equals to wave period times square root of dx. In this form, so shallow water waves, this includes the water depth h. And c, this is a wave speed, wave propagating speed. This is derived from the square root of g times h. This means that the wave speed directly related to the water depth. Okay. Okay, with using this shallow water wave condition, we can calculate the tsunami waves. Okay, this is a practice 1, practice 3. Tsunami can be treated as a long wave. Long wave means shallow water wave, extremely shallow water wave. This means that we can use this form, okay, this form. The average depth of the Pacific Ocean is around 4,000 meters. In this condition, please calculate the speed of the waves traveling in the ocean with a depth of 4,000 meters. Okay. This is very easy. Wave speed equals to square root of dx, and you put 4,000 meters here. So you can easily get the speed of the tsunami, in this case, around 200 meters per second. 200 meters per second. Very fast, because 712.76 meter per hour. Sorry, this is kilometer per hour. Kilometer per hour. Sorry, kilometer per hour. This is nearly the same as jet plane. Sorry, this is kilometer per hour. So the next, so we talk about the physical values derived from the velocity potential. Okay. This is a solution of the velocity potential, and from the definition of the velocity potential, so U and W can be derived as these forms. Okay. And pressure. can be obtained by the Bernoulli's equation. So in this case, we now talking about the linear theory. So we neglect this part here. Square of u and square of w, we neglect this part. So from this assumption, so we get the pressure as this form. Okay. Okay. This relation include pressure due to wave motion here and pressure due to static pressure. Okay. So usually in case of no wave, only this part appeared. But when we talk about the wave, so wave component, it appeared on this side. Okay. These are the physical values of the wave under the wave motion. And next is the water particle motion under the wave propagation. So from U and W, so when you integrate U and W by T, you will have the displacement of the water particle from the original position, x0 and v0. By introducing the form of the U and W as derived in previous slide, okay, we will get xi and theta are expressed like these equations. Okay, this is a little bit complicated, but not so difficult. You can understand this. Just only integrating U and W. From this, maybe you understand xi square of xi equals to square of amplitude and square of sine function and square of this part related to z direction. And this summarized like this one in square of xi, and the square of theta in the same manner as xi, you can summarize the square of xi like this one. So from these two relations, we can easily understand square of sine function, a square of cosine function equals to 0, equals to 1 with using this relation. A xi, square of xi part and square of theta part equals to 1. A and B is defined like this one, like this. So this is a formula representing an ellipse. Okay, this means that the trajectory of the water particle is described as an elliptical motion. Okay? Elliptical motion. In shallow water case, you take this assumption, and in the case of deep water, you assume this assumption. So A and B can be expressed like this in case of shallow water, and A and B also expressed as this form in case of deep water waves. So when we draw these relations in the figure. So the shallow water motion, like this one, it has a elliptical motion, but the size of the horizontal axis is almost the same from water surface to the bottom. Because the this is a shallow water cases and water depth is very small relative to the wavelength. But on the other hand, in deep water case, it has a circular orbit like this one because A expressed as like this one and B expressed like this one. This is the same. A equals to B. Horizontal axis and vertical axis has the same value. This means that not a ellipse but circular. Okay. These are the wave motion under the wave propagation. Okay. So this is totally different from the river flow. River flow, in case of river flow, water particles flow upstream to downstream. But in case of wave motion, water particles never move with wave form. Okay. Water particles never move with wave form. The particle just moving as a elliptical orbit or circular orbit, never propagate with the wave motion. This is a large difference between river flow and wave propagation. So next is wave pressure. From Bernoulli's equation, you can get a wave pressure like this one. Hydrostatic pressure part and wave pressure part. So due to the wave pressures, here is a wave pressure part. And in case of wave crest, it has this kind of pressure distribution. And in the trough, at the trough, it also has this kind of pressure distribution. So around the around the hydrostatic pressures, wave pressure increase and decrease, changing periodically. Okay. From this relation, so we can measure the water surface by measuring the wave pressure. Okay. This is a waveform here. And measure water pressures at a certain depth Z equals to H1. This equation can be expressed like this. And this part is the same as this relation, so can be expressed as eta. This means that the water surface fluctuation eta is obtained from wave pressure value. When you measure the wave pressure P, so from this value, you can get the water surface displacement eta. Okay. So with using this relation, so we sometimes measure the wave height. Principle of water pressure type water level gauge. Water level gauges means the instrument that measures the wave height. Okay. Wave height is obtained by the wave pressure. Okay, today, so I talked around more than 60 minutes. And last one, so I want to introduce my recent research. Okay. So I'm now interested in the characteristics of wave run-up height and wind action. Okay. Characteristics of wave run-up height and the wind action. Okay. This is recent. This is my recent research topic. So, because huge coastal disasters due to storm surge or wave overtopping tend to occur frequently in Japan. So, maybe you don't know, but in 2018, we had a very huge typhoon attack, and Kansai Airport, the gate of Osaka, was flooded like this one. This is a very severe damage. This was a very severe damage. The airport closed for 1 week, more than 1 week. So, but of course, the seawall designed properly, but this kind of flooding happened. So I assumed that the current design method is not enough because it doesn't include the effect of the wind. Okay. So that is why I started this kind of research. So many researchers have been investigate the characteristics of the wave run-up height, but such kind of flooding happen frequently. So I think that the coastal disasters caused by high waves usually occurred under the strong wind, and unexpected wave run-up may increase damage. So I assumed that wind effect is more larger than we expected. So this study aimed to clarify the effect of the wind velocity on the wave run-up height observed on the revetment by hydraulic experiment with a two-dimensional wave flume. So we conducted the experiment with using two-dimensional wave flume, which has a function of blowing wind inside of the tank here. Okay, so this is a wave generator, and here is exhaust fan, and we control these wave generators and exhaust fan, and so we did experiment. The model scale was 1 to 45, and seabed slope is 1 to 10, and we change the slope of the revetment theta 20, 30, 40. And wave height changes 2 centimeter, 5 centimeter, 7 centimeters, and period changes from 1.0, 1.5, 2.0 seconds. And also, we changes wind velocities inside of the tank from 0 to 8.6. So this is an experiment. 8.6 meter per second. This wind speed is roughly equivalent to the wind velocity 24 meter per second in the field. This is an example of measurement on the wave motion on the slope. On the slope here, we measure the wave motion up and down here. And this is the result, up and down, like this one. Okay. This is no wind condition. And here is wind condition 5.6. there are small fluctuations on the water surface profile. So today, the time is limited, so I talk about full of this result, but this is a photo of a snapshot of the wave motion hitting on the revetment. Okay? And breaking of the wave and no breaking wave and partially breaking in front of the revetment. These are very important when we talk about wave run-up height. Okay, this is one of the slides I show you. The lateral axis is wind speed in the experiment, and the vertical axis is wave run-up height compared with no wind condition. In case of zero wind speed, of course, the vertical value equals to 1.0 because this vertical value is normalized by the run-up height in the case of the no wind condition. Of course, when we increase the wind velocity from 0 to 8.6, the run-up height gradually increases with wind velocity. Okay. But braking conditions are very important when we discuss the run-up height, characteristics of run-up. But this result says that wind speed increase, blowing wind increase the wave run-up height. In some cases, twice of the run-up height compared with no wind condition. Okay. So from these results, we confirmed that the wind velocity, blowing wind, is very important when we discuss the wave run-up. So that is why, now we are trying to find the formula can be used for the design of the sea dike or breakwater, which used for which used for the design of the wave run-up height, including the wind velocity. The current design formula doesn't include the wind velocity, but now we are trying to find the new design formula, which includes the wind velocity. Okay, there are some slides more, but today I will conclude my lectures. Firstly, I talk about the basics of wave motion based on the wave theory, and after that, I will talk about my recent research topics, which related to the design of the wave run-up height, including the wind velocity. Thank you very much. And I would like to close my talking. Okay. Back to the Mr. Ara. Mr. Ara.
Yeah, it's okay.
Mr. Ara-san. Okay, thank you very much.
Okay, thank you very much for your nice presentation. It's such an interesting presentation for us and very meaningful. And after that, we have about 20 minutes for Q&A session. To all the participants, if you want to ask something to our guest lecturer, you can click the raise hand button in your computer, then I will arrange the question for Mr. Professor Keisuke Murakami. And don't forget to introduce yourself for asking. So, any question for this session? Please click raise hand button in your computer. Okay. Please deliver your question, Mrs. Eva Rivi.
Thank you very much. Good morning, Professor Murakami.
Good morning.
I have a question about actually, this is the first time I got information about the basic of water wave. So quite interesting for me because I thought wave like what you call it, regular wave that but I saw last time that you explained that they also have like mountain, like the top of the mountain, like that. So actually the question is that when we, as a civil engineer, especially I'm from structural engineering, so I wonder about the how to about the
kalau nggak salah dia lagi ngejar S3 atau S2-nya gitu.
About how to design the height of the seawall, especially last time about your research, you also have you discussed about the wave run up height due to the due to the wind. So how to avoid something like that happen, especially like in your country in Kansai Airport? I think that's the question for me right now.
Yeah. Thank you very much. Thank you very much. So now, so in case of Japanese design method, so we use a formula. This is a very classical formula from the experiment. So for this several decades, so many researchers conducted the experiment. And from these experiments, so the national committees defined the formula which can be used for the wave run-up height design. But this is very complicated one. But so I will talk again. This is based on the experiment. So, but all these experiments are under the no wind blowing condition, because we have the wave tank which can blow the wind inside, but this is a new one from this 10 or 20 years. So this kind of wave tank increased, and many increased, but 30 or 40 years before, so we never used such kind of facilities. But the current design formula are established based on 30 or 40 years before experiment. So that is why the formula doesn't include the wind parameter. Yeah, that is one of the reasons why the Japanese design method doesn't include the effect of the wind. So, but now we are conducting the experiment under the wind blowing condition, and we try to show the difference of the wave runoff height between no wind condition and wind blowing condition. So based on these information, so I think that we can show the parameter, which estimate, which calculate the wave runoff height under the wind blowing condition based on the current conventional formula. So I never say the current formula is not effective. This is effective one, very effective one, but not including the wind blowing. So if we can introduce the parameter which can derive the wave runoff height under the wind blowing condition from conventional formula, this is effective, and this is very effective method. So I try to show this kind of parameter and how to introduce the parameter in conventional design formula. So this is my recent research interest. It's okay. This is a little bit complicated talking, but is it okay?
Yes. Because I know that Japan has many typhoons happen every year.
Yes.
Yes. So I also would like to know, in Japan, the civil design or requirement also designed to avoid the typhoon.
Yeah. Now, so yes, designed for typhoon in case of rough wave, because in typhoon attacking the some areas, wave condition becomes very severe. So based on the wave height, wave period, water depth, and the slope of the revetment, these are the important factors when we design the runoff height. These are the important factors. Of course, wave height is the most important factor, but I would like to say again, no wind velocities are included in the design parameter.
So you mean that the previous design doesn't consider about the wind velocity? But
yes.
They consider about the wind, but not the wind velocity, right?
Yes, yes.
Oh, I see. Thank you very much.
Okay, thank you, Professor Murakami, for your response to the question. And any other question for this session? We still have about 10 minutes in here. Anyone? You can raise your hand.
Yeah, I want to hear that. So today I talk about the wave theory, and but all of you are in the civil engineering department. So do you have the chance to hear the lecture about the hydrodynamics or fluid dynamics, or are there such kind of classes in your curriculum? No, no such kind of classes. Only structure or soil
No,
mechanics?
no. We have also hydraulic engineering.
Hydraulic engineering.
Yes.
Yes.
Hydraulic engineering. So you understand the continuity equation or momentum equation.
Yes.
Okay. And also the Bernoulli equation.
There's a lot of material that so interesting to we discuss more later, Mr. Professor.
But no lectures related to the wave.
No.
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 We don't have a specific class in wave.
Only river flow or something like that. Okay. Thank you.
Thank you, Mr. Professor, to have the presentation for today webinar. And I think it's enough for this session. And Mr. Professor Keisuke Murakami, could you please to deliver a closing statement in here?
Sorry, again, please.
Could you please to deliver a closing statement here?
Okay. Closing remarks. Okay. Okay. Today, thank you very much for joining this class. And I understand the topic of the waves are very, very new for you. But I think that Indonesia is the island country surrounded by the sea, same as Japan. So in Japan, coastal engineering is one of the important important part in the civil engineering, because we had many typhoons every year, and we suffer the wave disasters, high wave, tsunami, and typhoon, and storm surges every year. So, and also, only 30% of our area is flat, and 70% is a mountain. So this means that most of the people living in the low elevation area. Okay, maybe when you visit Tokyo or Osaka, these metropolitan areas are just 0 meter elevation, same as sea level, 0 meter, very dangerous. But in civil engineers design the sea dike or revetment and protect those important areas against wave. So that is why we can keep the safety area based on the coastal engineering effort. Okay. I think that maybe Indonesia is the same situation. Many people are living near the coastal area, and you also have the erosion problem or tsunami attacks or ground subsidence. And also you will have the sea level rise due to greenhouse effect. Maybe the situation near the coastal area getting dangerous more and more, I think. So in order to keep the safety area, so I think that the effort of the coastal engineers are very important. So I hope that some of you are interested in the coastal engineering, and some of you are interested in a study in Japan. especially in our universities, please contact me. Okay, please contact me. And thank you very much again today. Thank you very much. This is my closing.
Okay. Thank you very much, Mr. Professor Kisike Murakami, for delivering today material. And let's give applause to him. And okay, we will back to the master ceremony, Miss Helen.
Okay, thank you to the speakers for the delivery of their material on these occasions today. Hopefully, the material presented can be useful for all of us. Thank you also to Mr. Himamul Ala STMT as the moderator who has guided the material presentation sessions. As a form of appreciation, all participants are welcome to giving virtual applause. Okay, and the next we will enter to the documentation sessions. However, before that, I would like to urge today participants to fill in their attendance using the link that has been sent via the chat column. Well, ladies and gentlemen, I would like to invite all participants present to turn on their cameras and use the virtual background that has been provided. Here, I will guide the documentation session. On the screen, I can see 2 slides. Okay, ladies and gentlemen, I will start from the first slide. I will count until 3. 1, 2, 3. For the next slide. 1, 2, 3. All right, ladies and gentlemen, thank you. Thank you very much for your participations. The documentation sessions has ended. Finally, we have come to the end of the Civil Webinar 2023 with the 10 basics of water wave. Hopefully, what we leave today can be useful for all of us. On behalf of the entire organizing committee, we thank you for your participations and apologize if there are any shortcomings. I'm Helen Herista. As Master of Ceremony, today's event said goodbye. Apologize if there are mistakes. Thank you and good morning. Wassalamualaikum warahmatullahi wabarakatuh. Shalom, Om Shanti Shanti Om.
Thank you very much, Prof. Murakami.
Welcome.
See you again in Marang. Okay.
Yeah. We're waiting for you.
Okay. Bye bye.
Arigato gozaimashita, Mr. Professor.
Thank you very much. Terima kasih.
Terima kasih kembali.
Dalam pencapaian visi dan misi yang